My name's David Disseldorp. I'm from the SUSE Labs file systems team, and I'm here to talk about a project I've been working on, which is lklfuse. So, Linux file systems in user space with lklfuse. So first off, the motivation for the project. So, quick video that was shared by Will Dorman. So this is a Chromebook. He's connecting a USB device with an ext file system image on there, and he's managed to get the Chromebook to reboot just by inserting the drive. So in this case, he mentioned that Chrome OS was mounting with panic on error with ext file systems, and that was then obviously allowing him to trigger this reboot. So this isn't basically an exploit per se, but this is the sort of issue that we have with USB storage and what we hope to tackle in with projects like this. So there are quite a few problems with USB storage. So obviously everyone has them sort of lying around, and often you don't know where it's from. You may have got it at a conference, so you don't know sort of the supply chain of where it came from. You use it in all sorts of situations, like, I guess worst case, it's a public photo kiosk. You could be using it with, or lending it to your friend. You don't know whether they have a safe or up-to-date system. So these are the problems we have today. Steam and centrifuge, hopefully some of you know the reference. So that's the Stuxnet worm. So probably, I guess, shows how damaging the wrong USB storage can be. Mitigation measures. So obviously in this case, we have a physical barrier for insertion. It's sort of a bit brute force. So there are quite a few other options. So at the moment, in kernel land, we'd often just say, look, mount is privileged, so it's not our responsibility. But it's a bit more nuanced than that, in that most distributions offer a means to mount as an unprivileged user. So with OpenSUSE, we have udisks, which basically is the privileged service, which allows us to then request the system to mount the USB storage. That works nicely, but we still have this privileged service, and we're still obviously going through or feeding our potentially untrusted device into the kernel. We have Lux dmcrypt, so that's great for your Linux systems, but if you want to connect that or share that with others, then obviously you need driver support on all of your systems, which often isn't the case. Another cool Linux kernel feature is this USB authorization. So I think that's used in a couple of distributions anyway. They have this USB guard service which runs in the background, and you can then sort of set policies based on the devices you have, and that can then sort of handle the authorization as you connect. Within BIOS as well, that's of course an option just for basically disabling it so the operating system doesn't see those host ports. So then within Linux, or within the operating system itself, we can also run things like libguestfs. So this is sort of a more heavyweight virtualization or virtual machine, which then can be plumbed straight, or the USB device can then be plumbed into, and that can then expose it to the host. And finally, lklfuse. So this is also Linux kernel based. It's a modification or a new architecture or virtual architecture within Linux. With that, we can run the kernel as an unprivileged user space process. And the ideal case there, or the prime reason for that, is that we can reuse the existing file system implementations in kernel. We don't need to sort of write anything new, and they just run as an unprivileged service. So quick demonstration first off. I've just got the factory package installed on my laptop. So I'm just, actually, perhaps first I'll just show you what comes in the RPM itself. So yeah, it's really quite simple at the moment. We basically just have the UDEV functionality to filter for USB devices. We have a filter based on the file system on the device as well. So UDEV already can tell us which file system is on there. And then we're starting this from UDEV. We request that the lklfuse mount service starts. That runs the lklfuse process, and it runs it as then an unprivileged lklfuse user. So, log. So I've got this device. It sort of looks like I found it in a car park, but it's actually legit. And there we go. So here we've waited for the UDEV event to come through, and then basically lklfuse has started. So I'm sure you know regular boot messages for the kernel, but down the end you'll see that we have the ext4 file system mounted, and then with Fuse on my host system. We can then see that it's exposed to the host via this mount point. And we've got some data in there. We can, so that's basically how it's used. Yeah, so it's based on the Linux kernel library project. So it was started quite some time ago by Octavian Perdilla. So back when he was at University of Bucharest, he worked on this project. So it's still, I would say, mainly driven by him today. There's a GitHub project, and it's implemented then as a separate or a new virtual architecture similar to UML. So UML is this user mode Linux, which has also been around for some time. But lkl is much lighter weight than UML in that it doesn't support running user space processes. It's single CPU or single virtual CPU, no MMU. So we don't have virtual memory mapping. We don't need address space separation or protection within, for what we're using it for, we're basically having it mount and expose a block device. It's quite portable as well. So this is in contrast to UML. lkl runs on all sorts of systems. So Linux obviously runs on Windows, BSD, Android. So there are even some ports to things like UEFI bootloaders. I think Octavian also got it running within the NT kernel itself. It's just got this host operations API, which is then needed or needs to be provided by the underlying host system. The kernel threads run as regular threads, so there's no preemption, which means that there are some modifications for if there's say a loop which depends on a hardware interrupt, so say based on jiffies, then there are some extra changes in there. I think only a couple of them to basically yield to ensure that we don't get stuck in these kinds of loops. So as an application, there's basically you're linking against this liblkl, which is provided from the kernel build. The build itself also does generation of the header files for lkl. So these are auto-generated with basically an lkl prefix, so you're not colliding with host headers. Then basically, aside from sort of the lkl specific stuff to get the kernel running, so starting it, we then just use the regular syscall API. So lkl also provides a few other tools for testing and benchmarking. So there's a hijack library, which is quite handy if you want to run an unmodified binary and plumb that into lkl, and you can specify sort of the devices you'd like and IP addresses, things like that, and run it under LD preload. There's obviously the ability to plug block devices in. Uses basically a VirtIO driver. So there's a VirtIO MMU, which is used for the communication between the lkl kernel and the host driver. It supports network device pass-through for TAP devices, a few others. PCI device pass-through, I haven't actually played around with that, so that's allows for passing through VFIO PCI devices. And then with lklfuse, you've already seen what it does. We can mount using those file system drivers within lkl. We have fuse operations, so basically it uses or is built atop libfuse 3. The fuse operations are basically just direct calls into lkl. As you saw as well, it's at least on OpenSUSE, we integrate it with UDEV and systemd. We don't really need to make other modifications to the system aside from this allow other mount options. So basically fuse by default won't allow access to users other than the user that mounted it. In this case, we have this lklfuse user performing the mount, so we need to tell fuse to permit access from other users on the system. A few other use cases potentially. So obviously for testing, it's great because you can make changes and spin up the kernel really quickly. Also, for us, aside from just the security aspect of the project, it's also potentially useful if we deprecate or remove support for individual file systems. Then we can also, say, ship an RPM to allow customers or users to still access those old file systems. So quick look at architecture, just to sort of compare how it looks between your regular host and lklfuse. So basically we have the USB storage device plugged into the host. We get the UDEV event, which then basically also communicates or notifies UDisks about this device as well. And then as a user, we get the device notification where we can tell UDisks to mount it. And then we have our application just sitting on top in user space, interacting via regular syscalls with the file system. So lklfuse, there we have obviously a bit more complex stack. So here we have the, right down the bottom, we have the host kernel. So we're still getting this USB device notification. And basically with that, we're telling UDEV to configure the owner of the device node. And we're starting lklfuse and setting up this VirtIO block device to interact or allow lkl to basically interact with the block device. And then on the lklfuse side, we have it starting the kernel, so calling into lkl to start the kernel, adding the Virto block device, performing the mount, and then as we wait in the libfuse event loop, we're then basically based on the event we get from, or the IO request we get through the devfuse from the host kernel, we can then call straight into lkl and then go through the storage or the file system and block layer of lkl through virtio down to the host block layer, and then finally out to the device. So it's, a bit more overhead, obviously. And that's, why I wanted to present some sort of preliminary benchmarks so we could get sort of an idea of what we'd be looking at, or what could potentially be, I guess, tackled first in terms of improving performance or profiling. So I just, for this one, just grabbed one of the Orthos hosts with Tumbleweed. In this case, I was using QEMU USB storage devices, which I could then set up as RAM backed, basically just ensuring that I don't have any bottlenecks on the USB device side. And then I was comparing the XFS kernel mount or the FIO benchmark running on an XFS kernel mount versus using the Tumbleweed kernel versus a mount going via lklfuse. So I had a 4-core VM with 4 gigs of RAM, and then my workload was basically buffered read-write to a 10 gigabyte file on the file system. I wouldn't draw any expectations based on the numbers I'm presenting. So these are very rough early stages. So I think it's more just identifying where we can potentially look in future in terms of where to profile and look closer. So on the sequential read side, so you can see that for the 1 meg IOs, we're sort of sitting at around a third to a quarter of the performance with lklfuse versus the host kernel. And then as for the 4K IOs, we obviously then drop off quite a bit further. One thing to note though with sequential IO is that we're then also seeing probably the behavior of merging of requests at the block layer. So that may explain why I'm seeing such high throughput for the 4K write on the kernel with 4 jobs. And then a quick look at the latency distribution. So also, I guess, as expected, we were seeing quite a flat distribution for lklfuse. It's very dependent on host and lkl scheduling. Whereas with the kernel, we have sort of quite a spike of latency, all sitting at around the average of, 48 milliseconds. And lklfuse averages then around, that was 8 milliseconds, and 33 milliseconds average for the lklfuse. Right. I also saw some weird outliers with the kernel for the write, so something further to investigate, I guess. But again, a very flat curve for lklfuse. Nothing sort of to go on there. So at SUSE, I've mostly been focused just on packaging testing with XFS tests, so modifying XFS tests to ensure that it runs on lklfuse. There are quite a few changes, just basically ensuring that we can run the file system specific tests for atop of lklfuse and use the file system or native FS file system progs for MakeFS. And yeah, I've rebased it basically using the upstream patches atop the SLE15 SP6 kernel. And that's what I'm currently shipping, just so I had sort of a stable baseline to go on for comparison. Yeah, I guess at this point, we're sort of at the stage where it'd be helpful to know whether other users or customers would potentially find it helpful, or whether we should do other things or look at other options for mitigating this issue. Yeah, upstream itself, so it tends to sort of drag a little bit behind mainline. At the moment, it's sort of a fair way back at 6.6. So yeah, it does use some of the arch hooks from Itanium, which have since disappeared. So there's a few minor changes to sort of bring it back up to or closer to mainline. In terms of getting it into upstream kernels, so there have been, I guess, two main attempts. So Octavian, in I think it was 2015 or so, he made some effort to at least propose it upstream, and yeah, didn't get a super helpful response, I guess. And since then, it's Hajime Tazaki. So he's also one of the alcal project maintainers, and has also made quite some effort on trying to get it in a state that it's ready for upstream. So he then focused, based on feedback from the user mode Linux guys, he focused on sort of more integrating it into UML. His last effort, though, was still, I guess, a few years ago, and it tended to sort of stall at that point. But since then, we've also had interest from others in file systems teams, so just within the kernel community. So yeah, we're sort of hoping that others with interest from other groups, we can sort of hopefully get, eventually get some sort of upstream acceptance in bringing it forward. Performance, so yeah, they were very early preliminary numbers. So yeah, I think a lot more profiling, benchmarking is needed. I wanted to play around with the new fuse using IOUring commands. So I didn't benchmark with that because it's not in the libfuse library just yet. But it's now in kernel, so that'll be interesting to see and at least compare. And then documentation, so there's basically none at this stage. So yeah, a lot of work to do there. But otherwise, I think, yeah, we've got, I guess, 15 minutes or so for questions. I guess we'll stop the stream at this point too.